would be a continuation of what we have learned in the last class, namely electrowetting, its application, the new field of digital microfluidics, which has recently becoming more and more important, and we are going to concentrate more on the applications of digital microfluidics into various processes, and we will see how our basic understanding has been transformed into some unique applications in this interesting area of wetting. We know when an electrode is placed in contact with an electric field with an electrolyte and an electric field is applied, then let us say positive charges are going to accumulate spontaneously on the on the solid side of the liquid solid interface. As a result of which it is going to induce, it is going to attract from the electrolyte negative charges, and they are going to accumulate on the liquid side of the liquid solid interface. So, ideally it would look something like this. Let us say we have the electrolyte, the electrode, and an electric field is placed and there would be accumulation of some charges, let us say positive charges on the solid side of the interface, and a droplet of an electrolyte is sitting on this electrode. So, the negative charges will spontaneously be concentrated near the liquid side of the liquid solid interface. This would result in a change in the surface energy, and the equilibrium, and to achieve equilibrium the contact angle will reduce and the droplet would spread. So, that is the basic concept of electrowetting, and what we have seen in the last class is that there are ways to quantify the changes in the energy. We have taken recourse of minimizing the free energy of the process, since the accumulation of charge is a spontaneous process. This would be associated with a reduction in the Gibbs free energy of the system, and the equation from that equation two well known relations, Laplace equation and Young's equation, can be obtained, and finally incorporating the concept of electrowetting, the following equation has been derived, we have seen this class, where cos theta is the angle, it is essentially the contact angle on application of voltage, theta y is the contact angle at equilibrium contact angle without any voltage, and u is the applied voltage, sigma is the surface tension, d is the thickness, and so on. Now, when we saw this equation for the case of electrolyte in contact with an electrode, in direct contact with an electrode, which is electrowetting, we saw that the amount of voltages, the amount of potential difference that can be applied between the electrode and the electrolyte is rather small. It is only of the order of few hundreds of millivolts. So, the change in contact angle, though very fast, and the change in contact angle per unit change is voltage is large, we are limited by the voltage, the maximum voltage that we can apply in such a system, because if the voltage crosses, let us say few volts out of a few volts, then electrolysis would occur and the current would start flowing from the electrode to the electrolyte. So, the changes that can be brought by applying voltage in pure electrowetting is rather small. So, in order to move the droplet or produce any significant movement of the droplet, which is our basic aim in electrowetting, for electrowetting applications, that would not be possible with simple electrowetting. So, the new concept which has come in is to introduce a dielectric layer in between the electrode and the electrolyte. So, the dielectric layer is now separating the electrolyte, is not allowing to have any electrical contact between the electrolyte and the electrode. So, now you have the liberty to go for higher voltages, And since the capacitance of the dielectric and the capacitance of the charged layer very close to the electrode surface in an electrolyte are vastly different, then the equation has been modified in the following form as we see here. So, this is the Young-Lippmann equation for electrowetting on dielectric. So, what we see here is the same, that the change in contact angle with application of voltage. This is the equilibrium contact angle. The interesting thing here is the D in this equation is different from dH in electrowetting. Now, if you remember, in electrowetting we understand that the charges are going to be, the charges in the electrolyte are going to be concentrated near the interface, near the liquid solid interface. However, these charges, the distribution of these charges as a function of distance from the electrode is rather complex. Okay. There would be some sort of a distribution, but to incorporate this distribution into in a closed form in the equation, in any equation, would be difficult. So, the Helmholtz model has been assumed, it has been assumed that all the charges are going to be concentrated in a plane at certain distance which is equal to dH, the thickness of the double layer at some distance from the interface. So, this dH is generally of the order of 1 to 2 nanometer. So, this is only a model and it tries to depict a much more complex picture of the entire process by assuming that everything is at a certain distance from the interface. So, this Helmholtz model has been used, and in this equation what we see is that the D in this equation, the D what we see in this equation in electrowetting it's to be replaced by dH. Whereas, in the case of electrowetting on dielectric, the value of D is of the order of few microns. So, in electrowetting we get D of the order of 1 or 2 microns, whereas in the case of for electrowetting on dielectrics we get the value of D to be of the order of 1 micron, whereas the D for the case of electrowetting only would be of the order of few nanometers. Therefore, the value of the electrowetting number, which is denoted by eta, which measures the strength of the electrostatic energy compared to surface tension, it is going to be vastly different between electrowetting and electrowetting on dielectric. Let us see now the advantages of electrowetting on dielectric. We understand that since the electrowetting number is so different from that of the electrowetting number, in order to effect some contact angle change, equal contact angle change, you need to have a very high voltage for electrowetting on dielectrics. So, EWOD typically requires higher voltages to cause a change in the contact angle. However, you are not limited as in electrowetting to only a few hundreds of millivolts. You can go to 200, 300, 500 and you can therefore have a larger changes in contact angle, which is a prerequisite for the movement of droplet from one point to another, which we will see and discuss in this class itself. So, what is the limit? Can we go to 1000 volts, 2000 volts and have a change, complete change? Can we make a droplet like a thin film? Well, there are two problems. The first thing is dielectric breakdown. Each dielectric, depending on what is the material of that what is the material of the dielectric and what is the thickness, can withstand a certain potential difference. If the potential difference crosses that value, then we start to have current passing through the dielectric, which is known as dielectric breakdown. Now, when that dielectric breakdown takes place, that dielectric would be unusable. We cannot use the dielectric again for EWOD, any EWOD applications. So, we are limited by that, but people have reported voltages of 500 volt across the dielectric without having dielectric breakdown. So, by increasing the thickness or by choosing the proper dielectric, we should be able to operate at even higher voltages, but everything comes with a price. So, if we increase the thickness of the dielectric, then in order to change the contact angle by certain amount, you require even higher voltages. The second one is known as contact angle saturation. What we saw is that there is a parabolic relationship between the voltages applied and the contact angle changes. So, if we look at this figure, we can see that the variation of cos theta with the applied voltage u, and it follows more or less Young-Lippmann equation up to certain voltage, let us say when the voltage is about close to 280 or so. But if I increase the voltage beyond that value, then you would see that the contact angle becomes more or less independent of increase in applied voltage. So, this specific phenomena is known as contact angle saturation. So, we can go only up to certain voltages, and beyond that either it would be the case of dielectric breakdown or it would be a case of contact angle saturation. So, therefore, it's common knowledge that you can never make a partially wetting droplet to completely wetting. Okay. So, before you do that, you are going to hit the phenomena of contact angle saturation, and I must say here at this point is that the contact angle saturation phenomena is still not well understood. So, we are now going to with this background we are going to start this class with complex surfaces and droplet morphologies. How the complex surfaces would give rise to motion in the droplet. So, we know that hydrophobics, there are cases where hydrophobic surfaces with a strip of variable wettability can be used to move a droplet. So, let us say we have a surface in which the hydrophobicity keeps on changing. So, as I move, the surface becomes more and more hydrophilic. So, if I have one strip which is highly hydrophobic, the next strip slightly less hydrophobic, and so on. So, as I move in this direction, the hydrophobicity decreases. So, this portion is truly hydrophilic and this region is hydrophobic. What we see is that if a droplet is kept here, then the natural tendency of the water droplet would be to move in this direction. So, if I can provide the right value of hydrophobicity gradient, then there are reports that the droplet will move in the direction of more hydrophilic regions. So, this is one way by making the droplet move, but as you can see it is difficult to achieve, and the velocities that you are going to get in using such a process is rather small. People have also worked with patterned electrodes, and by patterned electrodes I mean when you have patterned separated by dielectric layers, and this is something we will see in greater detail in the next class, in the next slides. There is another thing is we can induce super hydrophobicity, and super hydrophobicity where typically the theta value could be of the range of 150, and this is something which requires some more analysis and study. So, topographically patterned surfaces can give rise to drastically different values of hydrophobicity, and this could be beneficial in many cases as far as droplet movement is concerned. So, I bring you to the next topic, which is two extremes. How would a droplet behave when it is placed on a topographically modified surface? So, we all have seen what would happen when raindrops fall on a lotus leaf. The lotus surface of the lotus leaf is not smooth. It has certain cilias. Cilias are nothing but vertical pillars which are embedded on the surface of the lotus leaf. So, these are the cilias, and when the raindrop falls on the cilia, it is not going to wet the region in between the cilia. Therefore, thereby the raindrop will never come in contact with the surface of the leaf, rather it would suspend on the cilia. Therefore, if you just tap the lotus leaf, the raindrop will simply roll away. So, the ease of movement of a raindrop on a lotus leaf is a perfect example of what would happen when the surface becomes super hydrophobic. On the other hand, you can have a situation in which, because of some geometric let us say considerations, the raindrop is not sitting on the cilia, rather it fills the spaces in between as well, and thereby coming in contact with the lotus leaf. So, these are two extremes. In one extreme, it is simply suspended on the pillars, so to say, on pillars on the surface, and in other case it fills the spaces in between the pillars as well. So, these two contrasting behavior of a droplet on a nanostructured surface is typically expressed either a Wenzel state, where the liquid fills the spaces in between, and the second is the Casey-Baxter state, where they are simply sitting on these pillars. Okay. So, if I think of the contact area, the projected contact area, which is simply this, and in this case this is the projected contact area. Now, if you compare the actual weighted area and the projected contact area, these two are different for both the cases. For the case of Wenzel state, the weighted area is more, the actual weighted area is more than the projected weighted area, whereas for the case of Casey state, the actual weighted area is less than the projected weighted area, and these two cases would give rise to two different laws. So, so if you see that in figure A, in Wenzel state, the roughness increases the actual liquid solid interfacial area, which we call as ASL, in comparison to the projected area, which is denoted by ASLP. So, there is a relation, famous relation, which is a phenomenological relation. So, it cannot be derived as such, but a large number of experiments support the existence of such a law, which is known as the Wenzel's law, which denotes the contact angle as a function of the equilibrium contact angle, and this factor R is the ratio of the areas. So, this is the actual area, the weighted area, and this is the projected weighted area. So, this is the area which would be wet if there are no structures on the surface. So, the value of R for the case of Wenzel state would definitely be more than 1. Now, if you look at this equation, you would see certain interesting things, and which would give rise to which will give rise to a concept that may have certain applications in areas. Now, you can see by looking at this equation that the contact angle on a rough surface will increase depending on whether your equilibrium contact angle is greater than 90 degree or if it is less than 90 degree. So, what you see here is that if let us say the contact angle is more than 90 degree. So, it is a hydrophobic surface without any superstructures on it, without any structures on it. Now, what you do is you provide structures on it. So, the value of R is going to be greater than 1 and this theta y is greater than 90. So, what this would provide is that the cos theta will increase. So, providing superstructures, providing structures on the surface which is inherently hydrophobic will enhance the hydrophobicity of the surface and vice versa. which is very important and interesting. So, this would tell us that the microstructuring a surface amplifies the natural behavior of the surface. So, if you have a hydrophobic surface and you provide such structures, then the surface will become more hydrophobic. If it is hydrophilic to begin with, then providing these structures will increase the hydrophilicity of the surface. So, this is the beauty of the Wenzel's law, because it tries to it describes two different behavior of the surface when you provide superstructure, when you provide structures on it. So, the superhydrophobicity can be explained by Wenzel's law. Now, let us think of the Casey-Baxter state, where we know that ASL is dramatically reduced and much of the apparent solid liquid interface is in fact a liquid vapor interface. So, this droplet is, you can think of as if a large portion of this droplet is sitting over an air water interface rather than a water solid interface. And you can well imagine that this reduces the friction between the droplet and the solid surface considerably. So, if the friction gets reduced, then it would be easy to move the droplet from one point to another. So, the roll off angle, which is defined as the tilt angle at which a droplet sitting on the surface begins to roll off, that would be lower for the case of Casey-Baxter state compared to that of Wenzel's state. And this high mobility and small contact angle hysteresis, as can be observed in Casey-Baxter state, has certain uses. And there is also a phenomenological equation which connects the contact angle, which is theta, with the equilibrium contact angle, and F is the fractional surface area of the pillar tops. So, the pillars which are provided on the surface, the area of the top of those pillars is denoted by F, and this equation is the Casey-Baxter state. Now, there is also some interesting studies which are going on to predict that a priori is it possible to predict whether a droplet on such a surface is going to behave as if it is in the Wenzel state, or it is going to behave as if it is in the Casey-Baxter state. Till today, there is no definitive theory which would predict when it is going to be in the Casey state or when it is going to be in the Wenzel state. But there are certain observations which can be made based on molecular dynamics simulations and experiments, which tells us that the behavior of the droplet vis-a-vis these two states would depend on what is the aspect ratio of these pillars, the spacing between these pillars, and the interaction denoted by the contact angle between the liquid droplet and the solid droplet. So, obviously, if your pillars are closely spaced, the chances are that you are probably going to get a Casey-Baxter state. If the pillars are widely separated, you get Wenzel state. Okay. If the height of the pillar is more, you would most likely you are going to get Casey state. If the attractive force between the liquid molecules and the solid molecule is high, then it's likely that the liquid will fill up the spaces in between the pillars, thereby giving rise to Wenzel state. But there is no definite theory which would allow you to calculate or to evaluate whether you are definitely going to get this state or the other. And in many practical situations, the situation would be something in between the two. Now, we are going to concentrate on practical aspects or the practical aspects of the dynamics of a droplet on an electrode or on a dielectric. Now, if you see this figure, the left hand side is one electrode where it is kept at 0 potential, 0 voltage, and the right hand side is another electrode which is switched on, and the droplet encompasses both the electrodes. Now, when this is switched on, this electrode is switched on, the contact angle will reduce and the contact line, the edge of the droplet will have a tendency to move in this direction. So, if the conditions are right, then mass from this portion of the droplet will move towards the adjoining electrode, and the entire droplet will probably shift from the left to the right. So, by choosing the activated and the deactivated electrode and by operating at the right voltage with the right separation in between the two electrodes, the droplet can be made to move from one electrode to the next electrode. So, this is the concept, but there are certain problems associated with, there are certain interesting phenomena associated with movement of the droplet from one electrode to the other, which I have depicted in here. Now, this is a schematic view of an imbalanced droplet which is partially overlaps one electrode which is switched on and another electrode which is switched off. Now, the left droplet is dominated by contact line friction. So, this is the location of the contact line. Now, as the droplet tries to move, what would happen is the contact line friction may pin the contact line right at this point, thereby not allowing the droplet to move in this direction. And on the other hand, we may have a droplet which is going to be dominated by bulk viscous dissipation inside the droplet. So, there are several contributions to the net force which oppose the motion. Now, if you have the contact line friction governing the entire process, then the pressure inside the droplet will equilibrate very quickly, and more or less the spherical shape will be retained, and it would be difficult for the droplet to move. Whereas, if your viscous forces are going to dominate, then you are going to have a sharp change in contact angle on the electrode which is switched on. So, you may have a situation in which the droplet, there would be flow in the droplet, natural flow in the droplet from left to right, and this would give rise to motion of the droplet in motion of the droplet from the off electrode to the on electrode. Now, liquid motion can also be achieved only if you cross certain threshold voltage. Okay. So, there would be some inherent inertia in the droplet which has to be overcome in order for the droplet to move. Now, this threshold voltage would depend on the nature of the surface, the thickness of the dielectric, the combination of the liquid solid, and so on. But in many cases, you will probably have to be up, let us say up to 50 volts before you can see appreciable change in contact angle, and thereafter you would probably see the movement. And the Reynolds number of such flows are can be evaluated to be quite small. So, if it is a small, for example, for the case of water, the velocities are going to be of the order of 10 to the power minus 2 to 10 to the power minus 1 meter per second, and we have droplet sizes of the order of millimeters, and the Reynolds number would be roughly about 100. Okay. So, the flow will mostly be laminar when the droplet moves on the surface. Now, this is a proof of concept experiment to test how EWOD works. Now, here you see that we have an electrode, and then this is the dielectric, and we have a thin hydrophobic coating on the surface such that the the droplet or the plug, as in this case, can move easily with less amount of contact angle hysteresis. So, a common hydrophobic material which is coated on the dielectric is Teflon, and this is a glass coated with Teflon, and some liquid is an aqueous solution of an electrolyte is sitting over here, and this forms a large contact angle. Now, when this electrode is switched on, you can see that the contact angle has reduced considerably, and the tendency of the liquid will be to move from left to right. So, a water droplet which was placed on the Teflon coated surface, in you can see that by applying a voltage of about 100 volts, the droplet is made to move from the neutral electrode to the electrode which has been switched on. Now, the coming slides are taken from a very interesting paper which has appeared in Advanced Matters in 2008, and this summarizes the present status of digital microfluidics as we know it. Now, as the two figures suggest, you can have a closed digital microfluidic system as has been as you can see in the left side of the figure, and an open digital microfluidic device. So, if you think of a closed system, then you have a number of electrodes which are embedded, and this is a glass cover, or it could even be an electrode, and a hydrophobic coating and a plug of liquid is situated over here. So, as these electrodes are progressively turned on and the preceding electrode turned off, the plug will move over the electrode in the direction in which the electrodes are sequentially being turned on. So, you have definite movement closed in a closed channel towards the electrode which has been turned on. Whereas, if you see an open system, a droplet sits over the electrode surface and over the dielectric surface, and it is exposed to vapor. So, there are certain advantages to this closed format of DMF and the open format of DMF, and we would see what they are. Now, this I have already described is the importance of the insulating layer, importance of the hydrophobic coating, and so on. The closed DMF devices are very well suited for a number of droplet operations. You can move a droplet, you can split the droplet into two, and even you can merge two droplets to make one large droplet. Whereas, open DMF devices are not capable of splitting and dispensing as efficiently as in the closed DMF devices. However, they are very fast and simple mixing can be achieved in open DMF format. So, if you have two droplets sitting at 2 points, then they can be made to come close, merge, become a large droplet. So, one reactant 1 and reactant 2 can be made to come together, mix, and the reaction starts. The advantage here is that since the length scale is so small, the resistance to mass transfer would be extremely small, and the reaction would take place in such a droplet at a very fast rate, and you would be able to monitor the progress of the reaction from outside. The most common way to monitor such reactions could be using an optical microscope, using a fluorescence microscope. There are certain other advantage, depending on whether you call it as an advantage or a disadvantage, is the evaporation is possible from a closed from an open digital microfluidic system. Now, if you have a reaction which is going on in a droplet, and if evaporation takes place, that is basically definitely a disadvantage. But let us say you are using the droplet to cool a surface, so to cool a hot spot. So, in that specific case, evaporation from a droplet can be beneficial. So, depending on what application we are thinking of, the evaporation from droplet in an open microfluidic system could be an advantage or a disadvantage. This is an interesting picture where I would like to spend some time. Now, we would like to see how discrete droplets can be manipulated by electric fields to an array of electrodes. So, this checkerboard, the board that you see, I mean all these are individual electrodes. This is a large droplet of, let us say, an electrolyte, and you are first going to split this droplet, first going to extract a droplet out of this larger pool of liquid. So, what you do is you switch this on, this electrode is switched on where the other electrode is switched off. by switching it on at the right voltage for the right amount of time, a droplet, a small droplet can be spliced from the larger pool of liquid, and you simply get one droplet, and then the droplet is made to move on the electrode surface in a specific direction. The direction of the droplet movement would be governed by how you are switching this on and off. So, in order to bring it to over here, this electrode will be switched off, this would be switched on. The moment it comes over to this electrode, the next would be switched on and this would be switched off. So, you can have tangible movement of the droplet in a specific direction, and it comes to this point. Now, when it comes to this point, the middle electrode is switched off, the left hand side is switched on and the right hand side is switched on as well. So, part of the liquid contained in the droplet sitting on the middle electrode will move to the left, part will move to the right, and again with the right combination of voltages and time, you would be able to divide this droplet into two droplets, which are then again going to move independent of one another into paths programmed from outside. So, one droplet will move in this direction and the other droplet will move in the other direction. Now, here I have a reactant. I would like to, let us say for example, measure the content of something, let us say glucose into this droplet. Let us say this is a blood sample, and I have taken very small micro droplets of blood, created micro droplets of blood, brought it here, the reagent comes over here, these two droplets merge, and then this becomes a reactor, and the progress of the reaction and the outcome of the reaction would allow me to quantify the specific chemical that I am looking for, let us say sugar in this case, blood sugar in this case, and I would be able to measure the blood sugar in using such a droplet. The other droplet, which has travelled in a different path, will be made to come in contact with another reagent, which for example measures what is the urea content of the blood. So, this in essence is the concept of lab on a chip. So, on a small chip you can have several reagents parked at different points on the chip, and by splitting small droplets from a large droplet, relatively large droplet, and then again splitting that small droplet into a number of micro droplets, making them move in a specific direction, coming them in contact or letting them come in contact with different reagents, and monitoring the reaction of that reagent with that micro droplet of blood on a chip itself, on a small chip itself, you can probably make a number of measurements of chemicals, their concentration present in the blood. So, this has revolutionized, or this has the potential to revolutionize the testing, the assays that we do with biochemical systems. Now, the next is another interesting example of a droplet moving over an inclined surface. Now, if you see that this surface is not smooth, it is a curved surface. So, the droplet starts from here, and with the right combination of switching on and off of these electrodes and with the right voltage, the droplet will be forced to move in uphill. So, that is very interesting, like that the body force, the droplet can rise and it can overcome body force. So, you see that it is such a strong powerful technique for any assay based biochemical applications. Okay, it is straightforward, it is reconfigurable, and you can control everything from outside by simply writing a program in which way, in what sequence and to what value your electrodes are being switched on. So, this picture is I mean, if you look carefully, you would see there are a number of electrodes. So, it's again a checkerboard design where you have number of electrodes over here and here in the x and in the y direction, and the scale here is given as 1 millimeter. So, a droplet which is sitting on an electrode, but in contact with the adjacent electrodes, you can do so many operations on this. Okay. You can split the droplet such that part of it goes to the to this side and the part goes to the other side, or you can make the droplet to move in any specific path that you want, and everything you can configure, everything you can reconfigure, you can reuse the system as many times as you want, and you can do a variety of droplet operations on this surface itself. So, this is a unique thing, unique advantage of digital microfluidic systems, where a small drop or a small volume of liquid can be manipulated any way you want. So, this is a very strong and powerful technique. Now, some of the electrodes which are used, these are information about the material that are used for electrodes. The ITO coated glass is a very common electrode, and the insulating dielectric layer can be vapor deposited with these following chemicals. You can grow a silicon oxide on a silicon wafer, and the silicon oxide will act as the dielectric layer, and the advantage is that you can control the thickness of the silicon oxide, thereby changing the breakdown voltage, and you can tune it in such a way that you can operate a silicon oxide coated silicon wafer in electrowetting experiments over a large range of voltages. And the hydrophobic coating that you see generally on the surface are Teflon. There is a specific chemical, specific solvent which dissolves Teflon, which is a fluorocarbon. So, in fluorocarbon, Teflon powder is dissolved, and the dielectric is coated, spin coated with Teflon, and this enhances the contact angle, and this also reduces the sticking of the droplet on the dielectric surface. So, now the droplet is free to slide over the surface, and this provides more mobility, enough mobility or enhanced mobility on such surfaces. So, the coating of Teflon is extremely important. And the next figure which are shown here is very interesting. This is something which I have not covered. So far we have seen is that by applying an electric field, you would be able to change the surface energy, and when you change the surface energy, the manifestation of that is in a change of the contact angle. If the contact angle changes in a non-uniform way, in an asymmetric way, then the droplet will move to certain side. So, the same change in the surface energy of a surface can be brought upon by optics. So, there are certain optically active surfaces which when we shine light, mostly laser light on it, its surface energy changes. So, whatever we were doing with electric field can also be done by light, by shining light on a specific portion of the surface. So, let us say here in this figure you can see that a droplet sits on a surface, and some portion of it is, I mean, we shine a green laser on it. So, from a large droplet, exactly like what you do in electrowetting EWOD, you can extract a droplet, because the contact angle changes, and the tendency of the liquid would be to move from the larger drop to the region where the contact angle is less. So, by shining light alternatively at different points, you can make the droplet move with the light. That is fascinating. So, by shining light on surface, you can bring a droplet to that point. So, you do electrowetting, but that requires lot of planning, lot of fabrication and so on. You need to have electrodes probably embedded on the surface, embedded inside the surface photolithographically. You have to cover it with a dielectric, you have to cover the dielectric with a Teflon layer, so to a hydrophobic layer, and then you provide current and the droplet moves from one point to other. So, there is a flexibility, but still it's the path is going to be limited. Wherever the electrodes are, you can make the droplet move on in that direction only. But if I have an optically active surface, so the only thing I have to do is I have to shine light at a specific spot. The spot where I shine the light will change its energy, surface energy. The contact angle will change and the droplet will preferentially move to that spot. So, by shining a laser light, shining a laser on a specific point, you can, as if you can take the droplet in any path that you want. Okay. You switch off the light and the droplet stops at that point. You switch on the light and move the light, the droplet moves with the light spot, as the contact angle in front of the droplet keeps on changing because of shining of light. So, this has tremendous potential in terms of flexibility, in terms of having any kind of motion that you may think of on a surface. In fact, the motion of droplets or motion of particles when you shine light on optically active material has given rise to fantastic applications. For example, optical tweezers and so on. So, you have a surface, optically active surface, and you apply an electric field. The moment you shine certain portion of it with light, and if the conductivity, let us say, of that area changes, then you are going to have concentration of field, channeling of field lines towards that spot. So, the particles are then going to move towards that spot and will start depositing, will start accumulating in the area where light is being shown. So, as a result of which you can have some sort of a separation or concentration of particles, or you can bring a specific particle from the bulk to a specific point where you want it to be. So, the application of optoelectronics and into this field in digital microfluidics is enormous. Now, this I have already described, is that the example of lab on a chip and how you can move droplets and so on. So, I will move on to the next is the substrates that are used. It could be a transparent glass with ITO coated, having a thin hydrophobic layer, and the droplet edges must overlap with at least 2 adjacent electrodes in order to have any kind of actuation. And the typical droplet volumes which are encountered in these operations are between 0.1 to 1 micron per liter, 1 microliter. Now, if you look at this figure carefully, what you see here is what I was describing before: electrode number 1, electrode 2 and electrode 3. A droplet, the outline of which is by this white line, sits mainly on 1, but overlaps with 2 and 3. All are off right now. Suddenly 2 and 3 are switched on. So, what would happen? Some liquid will move towards 2 and some will move towards 3, and you get 2 droplets. Both the droplets are now on 2 and 3, however, overlapping with part of 1. So, from 1 droplet you have created 2 droplets. Next is everything is this 2 and 3 are switched off, but 3 is switched on, 1 is switched on. So, liquid from 2 will move towards 1, from 3 it will also move towards 1, and then you are going to form a large droplet. So, and everything is switched off. So, essentially you get back conditions in figure A in this case. So, you created 2 droplets and you merged 2 droplets. So, this has tremendous potential in as I mentioned in many applications, including these droplets behaving as microreactors. In some cases, especially in closed digital microfluidic systems, the droplets are suspended in oil. They prevent the suspension in oil does or fulfills 2 purposes. One is it does not allow any evaporation to take place, and the second is there are certain biofluids which corrode the surface or which deposits on the surface, and it is difficult to clean such a surface. So, if I provide an oil interface, droplets are suspended in oil, then these problems will not be encountered. However, the oil immersed systems have certain drawbacks, and I have listed some of them, that you would require special gaskets to contain them. There would be, if you have an oil droplet and a water droplet, then there is a possibility that the analytes will move from the water to the oil, and thereby you may lose certain chemicals and so on. And in some cases you require the drying of the droplets at the end of the experiment, which at the end of the measurement, which would not be possible if you have an oil based system. So, there are a number of applications of biological applications of digital microfluidics. So, starting from cell based assays to immunoassays and so on, which in the literature you will find a large number of such uses. In optical applications, I would only spend I will only say a few words about the micro lenses, because if you could create a lens using a droplet, a liquid droplet, the advantage is that it is very flexible, okay, and by applying the right electric field, the curvature, the contact angle, and hence the curvature of this micro lens can be modulated. So, you can vary the curvature by varying the contact angle and by varying the electric field. So, these are extremely sensitive control of the focal length of the micro lens made from a liquid droplet can be achieved in which have applications in display technology and so on. And one more application is, this is the thermal image of a laptop, the bottom of a laptop, and you can see there are certain regions which are very hot, certain regions which are cold, and if I would like to use the droplet for electronics cooling, you would see that this is the droplet. This is a hot spot, the whiteness shows the hot spot, and as the droplet comes to this point, the hot spot disappears. As the droplet moves away from it, you would see a faint reappearance of the hot spot. So, by controlling the frequency of the droplets, the velocity of the droplets, the hot spot generation on electronic chips can be controlled, which is a very interesting example of application example of droplet movement. And finally, one interesting unique example of DMF to close today's class. This figures, you can see there are 4 droplets. The droplets move simultaneously, keeping equal distance in between them. So, what is done is a thin sheet is placed on them, as you can see over here. So, now it acts like a conveyor belt. So, the droplets move with the equal velocity, and this also moves with the droplets, and therefore, if you can keep something on top of it, then the entire thing will act as a conveyor system. And this is what you can see in this figure, very interesting example. You see something, a black thing which is placed on the sheet, and the weight of this, you can see it has bent as well. If you know what it is, you will be truly surprised. This one is nothing but a ladybug which is carried on a silicon wafer supported by 4 droplets. So, an unique application of digital microfluidics to end the class, and this shows that you can truly do some really interesting and fascinating things with digital microfluidics, and the entire process is based on the concept of electrowetting or electrowetting on dielectrics. Thank you.